Namaskar dosto, get ready because today we are breaking down a force that literally drives our entire world. Welcome to this Concept Clear Explainer. आज हम बात करेंगे टॉर्क के बारे में या the real world magic of torque. From those heavy university physics textbooks straight to the cutting edge electric vehicles on our streets, we're going to figure out exactly how this rotational force shapes, well, pretty much everything. So let's just dive right in.
So, let me ask you guys something. आपने कभी notice किया है? Or maybe you've actually felt it yourself. Why does an electric car just throw you back in your seat literally the second you step on the accelerator? I mean, when you press the gas pedal in a regular petrol car, there's always this slight, noticeable delay, right, before the car really pulls. But in an EV, boom, immediate power. What's the secret behind this instant launch? Well, to figure that out, we gotta go back to the basics.
Section 1. Torque आखिर है क्या?
Okay, before we get to the farafat speed of electric motors, we absolutely need to break down the textbook physics. Think about turning a tight wrench. When you apply force to turn something around a pivot point, that rotational effect, that's torque. But here's the catch. Not all your effort actually goes into turning it. The force you push straight into the pivot, the radial force, doesn't help rotate the wrench at all. Zero. It's only the tangential force, the part of your push that is perfectly perpendicular to the handle, that actually gets things spinning. You sirf takat ki baat nahi hai, guys. It's all about exactly how and where you apply it. And that brings us to the actual vector cross-product formula from those trusty physics textbooks. Torque, which is represented by the Greek letter tau, equals r cross f sine phi. Now, don't let the math scare you. R is just the distance from the pivot, the moment arm, and F is your force. That sine phi part, that's the real game changer. It represents the angle you're pushing at. To get maximum torque, you want to push at a perfect 90-degree angle. If you push at some weird angle, a lot of your energy is literally just wasted. So distance, R, angle. Dono bahut zaruri hai. So another crucial point here is that torque actually has a specific direction. In physics, there's this simple rule of thumb for rotational direction. Counterclockwise motion creates what we call positive torque, while clockwise motion generates negative torque. Honestly, just think of it like opening or closing a tight jar of pickles in your kitchen. Cool na? Turning it counterclockwise to loosen that stubborn lid is our positive direction in rotational dynamics. Band karna. Twisting it clockwise to seal it is our negative direction. Pretty simple, right? Now, how do we take this from a simple wrench to, say, a speeding car? Well, when a wheel rolls perfectly on the ground without sliding, it's actually a beautiful combination of two different things. The whole wheel moving forward, translation, and the wheel spinning around its center, rotation. So the total kinetic energy of the wheel is the sum of its translational kinetic energy and its rotational kinetic energy. For perfect rolling without slipping, the speed at the outer rim of the wheel exactly matches the forward speed of the car's center of mass. This means the very bottom of the tire, the exact spot where it touches the road, is instantaneously at rest. It's kind of mind-blowing, but it's pure physics in motion on every single drive.
Section 2. Bolts or clamp load.
Let's pivot for a second to a micro, highly industrial application of all this. Have you ever wondered how engineers know exactly how hard to tighten a massive structural bolt? I mean, pura bridge a building in Petigaote. If you under-tighten it, it vibrates loose over time. But if you over-tighten it, boom, the bolt snaps. So engineers rely on a very specific formula to target a precise clamp load, ensuring absolute safety. The formula is T equals K times D times P. Here, T is the tightening torque you apply, D is the nominal diameter of the bolt, and P is the target clamping load, which is usually around 65% of the bolt's proof load. But you know what the real wild card is here? It's K, the nut factor. It's absolutely fascinating how simple environmental variables can completely change this K factor, and therefore the amount of torque you need. For instance, a plain dry bolt has a K factor of 0.20. But if you add some heavy lubrication, the friction drops, and that K factor plummets to just 0.10. That means you literally need half the torque to achieve the exact same clamping force. On the flip side, a hot dip galvanized finish without any oil bumps the K factor all the way up to 0.42. Basically, surface conditions like roughness, finish, lubrication, बदलते ही tightening torque requirement बिल्कुल बदल जाती है. It's a total game changer. Section 3. Petrol versus electric torque. All right, let's bring the conversation back to the macro scale to answer our very first question. Petrol versus electric torque. Dono गाड़ियां अलग कैसे perform करती हैं? Well, when we compare the engine ka chakkar objectively, the differences in energy usage are just massive. An internal combustion engine actually wastes a significant amount of its own produced torque just to keep itself running. It has to compress the fuel-air mix, eject exhaust gases, run fuel pumps, cooling systems, and overcome the heavy mechanical friction of its own gearbox. In stark contrast, an electric motor's torque is directly proportional to its electrical current. There are barely any self-maintenance losses. No pistons to pump, no exhaust to push out. It's just incredibly efficient. And because of all those moving parts and the nature of internal explosions, an internal combustion engine simply cannot deliver peak energy from a dead standstill. The RPM at the start is just too low. To get more power, you have to modify the fuel-air ratio and physically increase the frequency of those piston cycles. The engine has to literally spin up and build its RPM to reach its peak torque and power output. That whole process, drawing in air, injecting fuel, compressing it, igniting it, it actually takes physical time. And you guessed it, that is exactly the delay you feel when you step on the gas. But here is the truly mind-blowing fact about electric motors. Because torque in an EV is proportional to the current, and you can flood the system with electrical current instantly, an electric motor has 100% of its available peak torque, ready at exactly 0 RPM. Zameen par khade khade, bina engine rev kiye, you have maximum rotational force right at your disposal. This is exactly why an EV pulls you back into your seat the absolute millisecond you touch the pedal. No waiting, just instant power. Now, you might be wondering, is there any delay at all in an EV? Well, technically yes, but it is measured in microseconds, or at most a few milliseconds. The only real delay is the time it takes for the phase controller to distribute the DC battery energy into the motor's phase wires and for the inductance of the motor windings to build up the magnetic field. This happens so incredibly fast, well under the roughly 50 milliseconds required for human beings to even perceive a delay. So for us mere mortals, the acceleration is essentially instantaneous. Which brings us to our final thought for this explainer. From the careful, life-saving calculation of clamp load in a skyscraper's bolts to the millisecond phase controllers in our electric cars, the physics of torque is literally everywhere. So Dosto, the big question is this: how will this ongoing mastery of instantaneous power delivery continue to reshape the future of both structural engineering and our daily transportation? It's a pretty fascinating thought to leave you with, right? Thank you so much for joining me for this Concept Clear explainer. Keep wondering, and I'll catch you in the next one.